This is Lesson 5 in our Calculus 1 series, the Squeeze Theorem. If f of x is less or equal to g of x, which is less or equal to h of x, for all x near a, except possibly at a, and if the limit as x goes to a of f of x is equal to the limit as x goes to a of h of x, let's call that L, then the limit as x goes to a of g of x is also equal to L. So what we're saying is that if g of x is stuck in between f and h for all x values surrounding x equals a, and the limits of f and h are both equal to L as x goes to a, well, then this limit's going to have to be equal to L as well. So let's take a look at this example. We want to find limit as x goes to 0 of absolute value of x multiplied by sine square 1 over x. Now here I see a sine function, and I know that sine values are always between -1 and 1. Now because we're squaring the sine values here, I know that's always going to be between 0 and 1. So right away I know sine squared of 1 over x is going to be greater than or equal to 0, less or equal to 1 for all x not equal to 0. We can't plug in x equals 0 here, right? So we have this inequality. Okay, let's multiply in by absolute value of x. We know that absolute value of x is a positive number, and multiplying by a positive will preserve the inequality sign. So that says that 0 is less or equal to absolute value of x times sine squared of 1 over x is less or equal to absolute value of x. Now we know the limit as x goes to 0 of 0 is going to be 0. And the limit as x goes to 0 of absolute x is also going to be equal to 0. That says the limit of absolute x sine square 1 over x as x goes to 0 must also be 0. And let's take a look at this graphically. Here are our bounding functions, y equals absolute value of x. This is our h of x in the Squeeze theorem. Y equals 0 is our f of x. And here's the limit we're trying to find, the limit of y equals absolute x sine square 1 over x. We're trying to show that this limit is equal to 0 as x goes to 0. Well, we can see by the graph that the graph of our function is stuck between absolute x and 0 always. And again, as x goes to 0, these two graphs have a limit of 0, so therefore our graph must also have a limit of 0. That's what the Squeeze theorem is saying. And keep in mind that the Squeeze theorem is particularly useful when we're talking about sines and cosines, because their values are bounded between -1 and 1, or when we square them, between 0 and 1. So that gives us a natural inequality to start with, and then we can modify that based on what we need, the way that we did here. Now let's take a look at limit as x goes to 0 sine x over x. We saw this in lesson 3, and we found this limit numerically. We took some x values that approach 0 from the left, and some x values that approach 0 from the right, and we computed their corresponding function values. And we saw that the function values went to 1 from both the left and the right sides. So we said that this limit is equal to 1. Now let's prove this limit algebraically using the Squeeze theorem. What we're going to show here is that sine x over x is bounded by cosine x and 1 for x near 0. And then we're going to show that the limit as x goes to 0 of cosine x is equal to 1. And we know that this limit is also going to equal 1 as x goes to 0. So therefore, sine x over x will also approach 1 as x approaches 0. So this is the inequality we need to do a little work to prove. And once we have that, then we have the limit we're looking for. So let's take a look at how we can get this inequality. Consider angle x with x between 0 and pi over 2. So let's take a look here at angle x. And let's take a look at the triangles we form here. We know that the area of triangle AOB AOB, triangle AOB, we know that that's less than the area of the sector AOB. So now we're talking about the circle sector AOB. So now we're moving along the circle. So we know that's a little bigger than the area of the triangle. And we know that that is less or equal to the area of triangle AOC, the big triangle here. Area of triangle AOB is going to be 1/2 base times height. So AOB, we know that the base is equal to 1. This is a unit circle. And the height is going to be sine of angle x. So 1/2 base times height is here. Now for the area of the sector AOB, we know that the area of a circular sector of angle theta and radius r is theta over 2r squared. So our angle here is x. So this is x over 2 times 1 squared. And then the area of triangle AOC is going to be 1/2 base times height. And the height here is going to be tan of x. We have an adjacent side of 1, and that's our opposite side, so tan of x is going to be this height over 1. So 1/2 base times height is here. So now we have this inequality based on these shapes here. And if we multiply this inequality by 2 over sine x, we know that sine x is positive for an x value between 0 and pi over 2. So we preserve the order of the inequality, and so we're here. And now taking reciprocals, we know we're going to reverse the inequality signs, and so that gives us the inequality we're looking for. And then we can apply the squeeze theorem to get that our limit is equal to 1 as x goes to 0. And graphically we can see here's y equals 1, here's y equals cosine x, those are the bounding functions, and here is y equals sine x over x for x values near 0. So by the squeeze theorem we have that the limit as x goes to 0 of sine x over x is equal to 1. And this is a limit that you want to remember and you're going to want to apply. Now I just want to mention this use of the squeeze theorem here to prove this. This is not an obvious proof, and I wouldn't have expected you to think of this on your own. But you should be able to follow all of the details that we've just gone through. Now you might be wondering, why is this better than the numerical method? Why did we want an algebraic method of proving this limit? Well, when we take limits numerically, we're approximating. And when we use algebraic methods, we're computing exactly. So going back to the table here, it looks like these y values are approaching 1 from both sides. And we're pretty confident about that. But really we are approximating. We don't know for sure unless we're finding the limit algebraically. So if we can take a limit algebraically, we always want to do that before we resort to numerical methods. Now keep in mind that this limit as x goes to 0 of sine x over x equaling 1 gives us a couple of other useful limits as well. There's nothing special about this x that's going to 0. So if instead we had a constant times x going to 0, and then that same constant times x here and here, the limit is the same. Doesn't matter what we call this variable. We could call it x, we could call it kx, we can call it 5x, 2x, 3x, doesn't matter. So anytime we see the same constant here, here, and here, this limit is also equal to 1. Also, if we take the reciprocal and we look at the limit as x goes to 0 of x over sine x, that's also going to equal 1. It's going to be the reciprocal of this limit, and so that's still 1. And then similarly, using the kx, we have this limit is equal to 1 as well. So when we have something like limit as x goes to 0 of sine 4x over x, it's not exactly the original limit, and it's not exactly this version with kx, so we need to manipulate it into this version. So we want this to say sine of 4x over 4x, and have the limit as 4x goes to 0. So let's multiply in by a 4 over 4. Now we have sine of 4x over 4x, and this 4 can come outside the limit. So we're here. So we almost have what we need. We just need to be sure that as x goes to 0, 4x is also going to 0. And so let's think about that for a second. As the x values go to 0, certainly 4 times x is going to 0, and vice versa. So it's equivalent to write limit x goes to 0 and limit 4x goes to 0. Those are equivalent limits. And so now we have this set up as exactly what we need. So this is going to be 4 times 1, and this limit is equal to 4. Let's take a look at another. Here we have limit as t goes to 0, sine 2t over sine 6t. So the first thing I want to do here is separate this into two fractions, sine 2t over 1 and 1 over sine 6t. Because what I'm hoping for is to get a 2t in the denominator here and a 6t in the numerator here. So we're going to multiply those in, but we need to make sure we compensate in the numerator and denominator. So we need to compensate for this 2 by multiplying by a 2 out front. And we need to compensate for this 6 by multiplying by a 6 in the denominator. The t's compensate each other, right? We have t over t here. So this 2 6 can come outside the limit. And now we have limit as t goes to 0 of sine 2t over 2t multiplied by 6t over sine 6t. And so we should separate those into their own limits, and just to be formal, we should recognize that the limit as t goes to 0 is the same as the limit as 2t going to 0. And then so we can solve this one, and that's a 1. Similarly, limit t goes to 0 is the same as limit 6t goes to 0. So we can solve this limit, and that's a 1 as well. And so this limit is 2/6. Take a look at another. Limit as theta goes to 0, theta plus tan theta over sine theta. Well, I see a theta over sine theta, so the first thing I'm thinking is maybe I can separate this into two separate fractions. So let's make this theta over sine theta plus tan theta over sine theta, and take the limit of each of those. And remember, we can separate this into two separate limits if they both exist. So this is conditional on both of these computations existing. So let's see if that works. Well, we know this first limit is equal to 1. That's the limit we had above. It's the reciprocal limit. And here we have limit as theta goes to 0 of tan theta over sine theta. Well, this is sine theta over cosine theta times 1 over sine theta. And so these sine thetas cancel. And plugging in theta equals 0 here gives us a 1. So here we have 1 plus 1 is equal to 2, and that is our limit. And with this, we'll conclude our lesson on the squeeze theorem.